All right. Hopefully your quiz is going well, and hopefully you're not struggling too much. But if you are, this video, video might help you out with it. Um, so I still need to show you something new, but it's more of an extension of what we've done. You guys have actually been working with the Riemann sums and find those areas, and like I've been saying every video, it's really working with definite integrals. All right. So when I ask you to find the area underneath a curve between the curve and the x-axis between two spots, I'm asking you to evaluate a definite integral, and that's what theorem 4.5 is stating. As long as f is a continuous and non-negative on the closed interval a to b, then the area of the region is bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b can be described as that right there. Right? So notice how we're talking about the interval from A to B. So we're starting at A, which we treat that as the lower bound. Then the interval ends at B. Oops. So the upper bound is B. We're finding the area of the curve. So it's bounded by the graph of f, which is right there. And hopefully you guys make sense of what the dx represents. So it's nothing new to you. So for that one question, I think it's the third one, that's a point. This is what they're asking you to do. Don't worry about evaluating it. I just need you to be comfortable writing it out to make sure that you have that connection. Okay. So from there, we can also talk about some other properties. Let's talk about the definition of these two special definite integrals. So for the first one, it says if f is defined at x equals a, then the integral from a to a of f of x dx would have to equal 0. So what that means is that if you're trying to find the area of just like a point, well, that point doesn't have any area, because if you can think about what that graph would look like, you would have, let's make a crazy graph, something like that, right? And let's say this is where a is. This right here starts at A, ends at A. So the area of that line is 0 because it's not a 2D shape. It's a 1D shape. It's a line, so it doesn't have any area. That's why it comes out to 0. So when you see something like that, where the upper bound and the lower bound are the same, automatically just call it 0 and move on. The second one is if f is integrable. How do you think we say that? I don't think I've ever said that out. I don't think I've ever read it out loud. On the interval from A to B, notice that it's saying starting at A and ending at B. That's why they put the brackets on there. Then we can say this. And notice the change. So the first one is saying we're starting at B and then we're ending at A. Wait a minute. That's kind of the opposite of what we were doing earlier, because it should usually be for the integral low then high. But the way this integral is set up is that it has it backwards. It switches the order. So as a result, we are still talking about the same piece of the graph, but we have to interpret it differently, right? And hopefully you can make sense of why, if the upper bound and lower bound are switched, it would be the negative version of what it should regularly be, where the lower bound is the smaller number and the upper bound is the higher number. Okay? Because if you think about it with respect to, like, let's say it was a velocity function, Yeah, actually, yeah. Let's do that real quick. So let's say we're using the same graph, but now it's a velocity function, right? So now this is a, and now this is b. When you find the integral, you're multiplying what is time by velocity, and velocity multiplied by time gets you distance. Actually, doesn't just get you distance. It gets you something else. It gets you the motion, because remember, velocity talks about direction. So if you're moving in the opposite direction, then it would make sense that the motion should be negative as well, because you're moving backwards. All right. So that's why that negative sticks in there. So let me just clean this up and I'll be right back. Okay. So we talked about those two properties. Now let's talk about the other two. Theorem 4.6 is the additive interval property. So if f is integrable, integrable, one of those two, or three, I don't know, on three closed intervals determined by a, b, and c, then the integral from a to b of f of x dx should be equal to the interval of a to c of the same function with respect to x plus the integral from c to b of that same function with respect to x. So let's talk about why that makes sense. And as always, let's go to a visual. So if we have a function like that, let's say we have a, c is in the middle, and then b is over here at the end, right? If I talk about the integral from a to c, I'm talking about, if this is f of x, of course, I'm talking about the area here. And if I talk about the integral from c to b of f of x dx, then I'm talking about this right here. So it would make sense that if I'm talking about the integral from a all the way to b, if I can break it up into two distinctive parts, though, I can just add this and this to get all of that integral there. I'm sorry, all of that area. Yeah. Okay. So that's theorem 4.6. If I talk about 4.7, it's just two more. I say a lot. Theorem 4.7 states, if f and g are integrable on the closed interval a to b and k is a constant, then the functions kf and f plus or minus g are integrable on the closed interval a to b, and here's what it is. So for the first one, it's just stating that if you have a constant multiplier, what you can do with that constant is you can just pull that out and then multiply by the integral that of like the regular function you have. So let's say I have the integral from 1 to 5 of 3 times x dx. Well, I can say that's going to be the same as 3 times the integral from 1 to 5 of x dx, right? And if for some reason I knew like what this number was, then I could say that this question would be equal to 3 times whatever this number in that box was. And that's how I could evaluate that definite integral. Kind of like when you're working with derivatives and you had a constant multiplier, you can kind of just like pull that constant multiplier out and then do your derivative and then multiply back in at the end. It's the same idea. And similar to that, we have the sum and difference properties of definite integral. So here's what we know. We are told that as long as it's on the same closed interval, we can just add or subtract the two functions. So if you can imagine what this looks like, keep saying, right? Let's say this is where our graph is. And let f of x be orange from A to B. So let's just make it a nice little straight line like that from A all the way to B. And let's have g of x be something else. All right. If I wanted to find the integral from A to B of the two functions added together, then what I can do is I can break it up and find the area of each individual function on that same interval and then just add those two numbers together. And let's talk about why that makes sense. That was a terrible line. Better. Needs improvement, right? So right there, that's what the integral from a to b of f of x dx would equal, right? If you notice, it encompasses all of g, and like that doesn't matter because I think about this as like it's overlaid on top of it. So when you, I don't know, copy an image on something, you can overlay or you can put it underneath it. Same idea. You can have them interact or you can just consider them two separate like images. And it's just that. So it would be whatever this is. Then whatever this purple one would be. Right? Because if I want to add them together, well, I take the area that a, like that function g encompasses, and then I would tack it on top of whatever area f of x encompasses from the interval from a to b, right? And if I want to subtract it, well, all I have to do is just take out that area, right? And that one right there would just be whatever this is. And that's it. Those are the special properties for the integrals. So tomorrow should ideally be a very easy thing where it's just a bunch of calculations as long as you understand the properties. You just do a little bit of multiplying, a little bit adding, subtracting, and you're done for the lesson. Good luck on your quiz.